Welcome everyone to another reverse engineering video. In this episode, we'll find another solution for the previous crackme exercise. Now we will start with its source code. Although we haven't seen the code, we were still able to reverse its logic using x64dbg previously. This source code is available on the GitHub repository, linked below. In this video, we want to find a flag with very minimal reverse engineering. This structure here corresponds to the node we reverse engineered manually before. Below is the list of nodes, each containing a letter and a pointer that links to another node. Very important, the first member of the structure is a char, but it will still occupy 4 bytes instead of 1, if you remember from the previous video. The flag checking routine is not complicated and it's based on a 10 characters flag entered from standard input. The flag is verified in this for loop. On a higher level, this is pretty simple. Something is read from standard input and is then being converted or modified in some ways, and then finally a flag is being computed. Alright, let's go forward. Okay guys, let's see what else. We have the correct password here. Keep that in mind or take a note somewhere, as you might want to test it later to see if it's correct. That's the branch for the correct message, and then the other one for the invalid flag. We will compile that using the GCC compiler, and then when we execute it, let's say we don't know the password, so we'll have an invalid flag message. If we open the file in IDA, we can get useful information about those two messages that we've seen before, those two branches. Notice that IDA displays the main function. We have the hello message here, and then this is the congratulations message and also the invalid flag. Enter Angr framework. Angr is a framework for symbolic execution of binary files. It does this by instrumenting the code and then systematically executing every possible branch. This framework is used a lot during CTF competitions, and it's good to become familiar with it. You can access the script on the referenced link. For now, let's focus on understanding the basic options to get started. First is the binary name. Then we specify the base address. Not strictly needed, but we can help correlate with other tools like IDA Pro. I've set it up as 0 here. Next is the option to automatically load external libraries. We set this to false to avoid external functions that might complicate the symbolic execution. Angr will replace library functions with dummy calls. The flag length we've seen before is 10, so we can define it here. Let's go back to IDA to verify this in the assembly code. Yes, this is the beginning of the loop we've seen before. It goes from 0 to 9, so we have 10 characters. We have also the format string showing that 10 characters are being read. The next option defines a variable. It's called flag and has size 8, which is the size of a char times 10, so we have 10 characters. Then we create a state and we specify that flag will be passed as standard input. Next we have this option, zero fill unconstrained memory. We pass it to the execution state. This basically means that all the uninitialized memory will be zero filled. It's not strictly needed here, it's more to have a clean state. Next we will set some preconditions on the flag letters, restricting them from between 0 and 9. This will speed up the execution and eliminate a lot of branches that don't lead to the correct answer. Let's make sure we can see those conditions in the assembly code. Let's analyze the blocks from the loop. var_4 is the counter for the iterations. This block over here converts the input letters from the flag from ASCII digits into integer numbers. We'll add any precondition to the script that restricts the flow towards the correct branch. So we know for sure that those characters should be between 0 and 9. We use state.solver.add function to add these conditions per each byte. Next, we pass that state to a factory method, which will create a simulation manager. Find address and the void address are two addresses that we want to either hit or totally avoid. They represent the two branches corresponding to the congratulations message with the address ending in 1229. And the other one for the error branch. Let's see what is the address. Go to this assembly view. So the address is 1227. Next, we will use these two addresses and start exploring, systematically doing the symbolic execution. At the end, we print the states found, meaning all the states that were terminated that matched the addresses conditions. Also notice that we need Python 3 to run this script. Python 2 is not recommended anymore. Make the script executable, start it, and let's see what happens. We will have to wait for a bit, but don't worry, the execution shouldn't take very long. Especially because we've added two very restrictive preconditions for the flag. Let's see how it goes. The answer should be found any minute now. If we're curious, we could even interrupt the execution and see how it progressed. The flag was found, 6 to 4, and so on. Exactly the same that we've seen in the previous video. Let's test. It's correct. I hope you see the difference between using Angr framework and the previous method that involved x64dbg. Although it is slightly more complicated to get started with Angr, it's a lot more automated and a lot faster. We don't need to do any heavy reverse engineering other than figuring out some basic preconditions related to the number of the characters in the flag and their possible range of values. We could even do symbolic execution without the preconditions, but it would take slightly more time. The more precise we are with the input, the better. I encourage you to check this framework and also see the examples on their website. This is really cool, especially if you're doing capture the flag exercises or plan to. Thank you for watching. If you like this video, send us your comments